And then most people got somewhere around 63.3. If you got 63.4, that was correct as well because of the extra rounding. So a few people got that. Some people, I think, just made mistakes in adding up their cycle length. So it's always something that's good to check. One thing that was good as well is I noticed some people created like Excel spreadsheets where they actually had calculations done for them and added in basically formulas to calculate the sum. So that was good as well. But one thing I noticed in general is people were adding the min time here. They're either in the 10-second min time or they're adding the 3-second extension to the cycle length calculation. So cycle length calculation does not include the min, initial green, or the passage time. It only includes walk, head clear, amber, and all red. So these 4 numbers here are what would constitute the cycle length on the main street, plus the cycle length on the side street. And if you have any left turn phasing, you'd add the, in this case, the initial green, since we don't have anything else, and the amber and the all red, but you would not add the extension time. Semi-actuated, so based on the ADT that is significantly higher along the main street and the fact that there's a pedestrian presence and that this is part of a coordinated signal network, I would tend to think semi-actuated is the best bet. There was what, 20,000, I think, on the main street. Oh, I don't have that in here. I think there was 20,000 on the main street, 5 on the side street. So I think that would be a good candidate for semi-actuated. Most people got fully protected. The main reason is because of the dual left turns. Also, if you have a speed limit of 70K or higher, you could argue that the fully protected left turn phase might be safer as well. So most people got that. Phase 5, again, that was something that some people got and some people didn't. But you got to remember that the main street phases will add up to 7. So if you have phase 2, it's going to be phase 5 that goes there, not phase 1, especially if it's an 8-phase operation. So most people got this timing chart filled in properly here. Again, some people added stuff to phase 1, but you shouldn't be. Bonus marks to anyone who put in extension times for 4 and 8. Once you realize that intersection was going to run semi-actuated, you would want to put extension times for phases 4 and 8. So bonus mark if anyone got that. I don't think I've seen anybody with that so far, but just to make that note. And then the phase recall menu. So far, most people have got this as well, but some people basically just copied and pasted what I had in the slide. So I'm going to go over that again tonight. But basically, you only put the check marks, X's or a check mark, in the area where you want to turn that phase on. And that's the exact same as with VSTRO. So we'll be going over that tonight. So again, the cycle length should have been around 63.3 or 63.4, and you would round that normally up in 10-second increments, so you get a 70-second cycle. Does anybody have any questions before I move on to tonight's module?
I have the question about the initial green for phase 2. So normally it's 10 seconds, but because phase 2 is they start with phase 5. So actually the initial green here, not minimum green, I think it will be 24 seconds.
So if you put 10, it was right. If you also put 18, which would be 7 plus 11, which is 18 for 2, and then this one would be 7 plus 14, 21 for phase 4. I wouldn't have marked that wrong. That's correct as well. So the walk time plus the ped clear really equal the initial green. So whether you put 10 or whether you put 18, it would be correct. But but it would not include the passage time, and it would not include the amber or the all red time.
I mean the green time, the initial green time of phase 2 only is equal to the other time of phase 5, 7 plus 3 plus 1, and then plus 10 of initial green here.
No, that would not be right. So even though phase 5 would come on at the same time as phase 2, the min time wouldn't necessarily be this plus the min time for phase 5. It could be that phase 5 and phase 2 come up together, and then if there's nobody on phase 6, then maybe it just rests like that, or goes to phase 4 and 8 afterwards. So I wouldn't. So if there's a left turn phase, I wouldn't add the time in the left turn phase to the initial green in phase 2.
Okay, I see. Thank you.
Yeah, Jeff, I have one more question. I thought that when a signal is coordinated, it should be fixed time because you don't want any lost time, or you want the coordination to flow, right?
Nope. often signals that are coordinated are fixed or semi-actuated. Semi-actuated, we'll learn about that next week. We're going to go over coordination, but in a semi-actuated location, the main street often gets more time. Any basically unused time would go to the main street in a coordinated fashion. But no, signals that are coordinated can be both fixed or semi. And for anyone who I have not marked, I just put some very basic comments on a couple of the ones that I did mark, but anything that I have not marked, I'm going to try and mark tonight. So I hope everyone should be able to get their marks by the end of the night. And if I screwed up your mark and I'm showing that you're only getting like 9%, then I'm going to fix that as well. I'm new to this whole grading things in my Canvas as well. It's a little complicated for the instructor, so I will get that fixed tonight. So I'm gonna close this window, I guess, if there's no questions. And can everybody see my screen here for traffic signal fundamentals?
Yes.
Okay, perfect. We'll start here then. So relevant readings for this module. Some of these pages in the Traffic Engineering 5th edition are very helpful, especially explaining some of the ring and barrier type scenarios. Some of the pictures from here and text are right in my slide today. So these are some good pages to read, not a lot of reading. If you can manage to read these 10 or 15 pages, which are mostly pictures anyways. Then again, the PTV Vistro has online resources. One I've already provided. It shows you some videos on Vistro. And then there's the help menu, which kind of guides you through Vistro as well. So hopefully people have at least opened up Vistro and checked it out, because we're going to be into it shortly. So ring and barrier diagrams. So based on the phasing diagram, there are prohibited combinations of movements. And then compatible phases are grouped together between the barriers. So if you see here in this picture that I've just got my mouse on, phase 1 and phase 5 have a green indication. Phase 1 and phase 5 are compatible, so they could go at the same time. In the diagram beside it, you'll see that phase 5 is red. There's probably no demand on that phase. So phase 1 and 6 go together. And if you think about that, if you're driving through an intersection, you'll see that sometimes when there are simultaneous left turn phases, they both come on at the same time, which would be shown on the street as green arrows where everything is red, else is red. And then sometimes you'll see the green arrow come on at the same time as the green ball. So that would be phases 1 and 6 moving together, opposed to just phases 1 and 5 moving here as well. So a barrier, a new term that we're learning today, is movements on one side of the barrier cannot be allowed on the other side of the barrier since they're not compatible. So you'll see in the diagram at the bottom here, there is barriers between phases 2 and 6 and phases 3 and 7. At no time would you ever want to have, in this case, the eastbound left coming on with the southbound through. So you never want the side street and the main street to have phases at the exact same time, unless you had an overlap, which I'll go over in a minute. So basically, the main street, phases 1 to 6, or phases 1, 2, 5, 6, and the minor street, phases 3, 4, 7, and 8, we're always going to have a barrier between them. So ring 1 is phases 1 to 4, and ring 2 is phases 5 to 8. So if you're using just phases 1 to 4, you'll have a single ring operation. And when you're using rings 1 and 2, you would have what's called dual ring operation. I'm going to explain this a little bit more on the next page. So here are some examples. So the one at the top left is a typical intersection with protected permissive left turn phasing in all directions. So you've got your basic phasing, 2, 4, 6, 8, and you've got the left turn movements, 1 and 5, 3 and 7. The stuff on the phasing on the left side of the barrier is the main street, and the right side is the side street. Then if you look below here, this would be a typical intersection with permissive left turn phasing. So if the phasing for the left turns is permissive, meaning that they just wait for a gap in opposing traffic, then you just leave these blank. So we've just got the through movements, and then these lefts, which are shown with dashed lines, are permissive. That means they have to yield to pedestrians. Now, if we want to look at the one at the top right, this would be an intersection with permissive main street phasing and split side street phasing. So this would be non-typical. This would be where you have phases 2 and 6, and then you have phases 4 and 8, and they're served separately. So this would be a bit more of a confusing type intersection. This would be in Vistro if you wanted 4 and 8 to operate separately, which would only generally happen if they maybe have dual turning movements or there is some sort of issue with the geometry. Then you would use split phasing. And then the one here on the bottom, again, is the same as the one on the top, except we're showing OA, which stands for overlap A, OB, overlap B, etc. So these are just showing the example of having a right turn overlap phasing. And we're going to we'll go through this in Vistro, which might make more sense once we're done this PowerPoint. So components of the signal cycle. So you've got the cycle, which is one complete rotation through all of the intervals. And then you have a phase. A phase is a set of intervals. So it's the green, or it's the walk, plus the flashing note walk, plus the amber and the all red. So the green or flashing or walk and flashing note walk could, so if the green time, let's say minimum green time is 10 and the walk and flash note walk is higher than 10, then you would go with the walk and the flash note walk. If the green time is higher than the walk and the flash note walk, you would go with the green. And then you add the amber and the all red, and that is one phase, which allows a designated movement or a set of movements to flow and be safely halted before a release of another phase. The total phase time is also called the split. So we'll see that word split later in this slide as well. And once we get into Vistro, you'll be looking at the split. So I've got the diagram here showing in the case of a left turn phase, you'd have the green time for the left plus the amber plus the all red. That is one phase. And if it's the case of a through movement with pedestrians, you'd have the walk plus the flash note walk, which would equal the green time, plus the yellow and the all red. So that would be, again, a single phase. And the cycle length, which we went over last week, the total time to serve all of the signal phases. So this is an exact replica of the slide from last week, so I'll be on this too quick, but basically just explaining cycle length and noting the recommended range is somewhere between 60 and 120 seconds. And when cycle lengths are above this, we can have a lot of delays. When they're less than this, we often lose a lot of time just to serving the ambers and the all reds. And that 90-second cycle length is often a good starting point when you're doing analysis. And again, we went over this a few minutes ago when I did the assignment marking. This is how you calculate the cycle length. So you'll see it here. We do not add in, if there is a walk and a flashing note walk, we do not add in the min time, and we do not add in extension times. So we're looking really at the time for the arrow. So you would in that case use that min time. But when you're calculating a through movement, if there's a walk and a flashing note walk, that time would usually prevail, and you would not add the min time to those when adding these up. And that would equal the minimum cycle length. So I'm just going to be quick with this because we already did this.
Sorry, Jeff, can you just repeat that again? So do not add the min time. That's the initial green time?
Yeah, so the initial green time or the min time, do not add that into the cycle length calculation when you're doing it for phases 2, 4, 6, or 8. In any cases we're going to be doing in class, I'm going to have pedestrian phases on those. So you would never use the min time for those. You would only use the min time for a left turn arrow. Okay.
And then, and the other one that we're not supposed to add in? Sorry, I have
the extension time. So the extension time, I think we went over that the very first class. So once a vehicle, so basically if we give a min time and a max time, in between there, we need to extend the time, usually based on the number of vehicles. So that's why we'll add an extension time in there. But the extension time does not get added to the formula to calculate the minimum cycle length.
Okay. All right. Thank you.
All right. So we're going to get into Vistro shortly, but before we do, I just wanted to make note of factors that affect the capacity at a signalized intersection. If you look at the picture above here, you might recognize it. It's a picture from Cambridge. Showing one of the more complex intersections there, and you can just see how many signal heads there are. It's a little bit confusing. The intersection's on a skew there. So when we analyze signals in Vistro or Synchro or any other type of software, some of the factors that affect how the intersection operates are the geometry. So of course, the number of lanes, the type, the grade, lane widths, lane utilization, lengths of storage bays, receiving lanes, Then of course you've got all the traffic conditions, which really are depending on all the different drivers. Everyone drives a little bit differently. So these software programs have to assume things such as vehicle flows, ped flows, cycling activity, parking, transit stops, peak hour factors. There's lots of different options. One thing that Vistro does not analyze is the effect of somebody sitting in their car texting as soon as the light goes green and they suddenly have a 10-second, they take 10 seconds to react to the green. So things like that are not in there, but we do put in as much data as we can to try and make our model accurate. We've got the arrival conditions, random or platooned arrival. So that depends on the coordination, which we're going to talk about next week. But if there are a lot of signals within close proximity to each other, we should have them all modeled together. That way we can model queuing and the metering and signal spacing together, opposed to just assuming if you just analyze one intersection all by itself, that's assumed to be random arrivals of vehicles. And then we got the signal conditions, which are the cycle length, green time, phasing, mode of control, lost time, and ped times. So the signalized intersection is the most complex location in any traffic system to analyze. The signal timing methodology requires a complex model that addresses all of the different variables. And besides fixed time locations, actuated locations require fairly complex calculations, and they are nearly impossible to do by hand because they would just be so time consuming. And as such, we're using software. So Synchro and Vistro, very similar programs. I have used both. They are classified as macroscopic analysis and optimization softwares, and generally they support the latest edition of the Highway Capacity Manual, which in this case is the 6th edition. But Vistro, you'll see, has a few different options. So one of those options is you can actually analyze intersections in the Canadian Capacity Guide. That's not really a common way that I've ever seen intersections analyzed, but certainly if you want to compare, you can model them in different ways. There's a few different options there. And the signal optimization routine, which are in these programs, assist us in creating efficient signal timing plans. That is really the purpose of the software. And a big note here in red that I'm going to show you guys a couple tools that you're going to find handy. One of them is basically clicking on an optimize button. But just remember that that's a starting point, and you can never really replace manual optimization, which is really just us reviewing what the program has done for us and then making fine-tune adjustments. So before you start analyzing anything in Vistro today, you're going to want to know the peak hourly vehicle volumes. So you enter the volumes into Vistro as an hourly volume. Normally, we would analyze AM and PM peaks. So you don't want to put the volumes in as, let's say, a 24-hour volume, because then your analysis would be screwed up. So you want to do it AM and PM. You usually want to separate those two peaks. Maybe you'd look at a different time of day as well. In my example today, I think I just noted it as the AM peak, but just the thing to remember is you're looking at the hourly volumes. You're going to want pedestrian volumes. You need to know what you're analyzing. So you need to know the geometry, basically how many lanes there are, what kind of storage lengths, what types of lanes. So you want to know that. You should really know your amber and all red times, and your pedestrian walk and flash and not walk times. If you start analyzing without this information, you're just guessing. And the more guessing you do, the more inaccurate your timing would be. You're going to want to know the minimum timing values that you feel would be safe, which we would find on those OTM tables. And if available, you want to know your current phasing, your max times, and your mode of control. But if not, you could use this software to actually determine those three items. So once you have entered all the different inputs into Vistro, that assists you in determining the recommended cycle length to achieve optimum performance. It will help you select your phase and max times for each phase. And it will also give you a bit of a heads up. You'll see if you're getting very poor operation, then you might need to consider additional phases. So I've done as an example, you could possibly add a protected permissive left turn phase if you see a really poor level of service for your left turn pocket. So if anyone wants to open up Vistro, I don't know if somebody, for example, has multiple monitors, you might be able to do both of this at the same time. So I'm just going to go over some of the settings you'll use in Vistro, then we're going to actually open it up and go over it again. But if anyone thinks it would be helpful, they might want to open up Vistro now. So the control type is important. That's going to be the type of phasing per movement. So it's going to default as permissive, but if you want to, for example, add a protected permissive left turn, you would change the option there. The signal group is just another word for phase numbers. Lead lag. So I'm not sure if anyone's heard of this word before, but that identifies whether the left turn phasing is leading, which means it's served before the through movement, or if it's lagging, which is served after the through movement. What do, somebody wants to maybe answer this for the class. What do you think most left turn phasing would be, at least in this part of the world, I will say, in like the Hamilton, Toronto, Ontario kind of area? What do you think would be the most common type of left turn phasing, leading or lagging?
Lead left turn.
Leading.
Leading.
Exactly. Lagging would be if the phase runs at the end after the through movement. So that's relatively rare. There are some issues with doing that. Plus, it's just not something that we would normally expect. We usually expect that the left turn arrow is at the beginning of the cycle. So most things you'll be doing will be leading. But if I do ask for something lagging, or you think there's a benefit to running a lagging phase, you can certainly make that case. But I would generally consider everything to be leading if possible. Min and max greens, amber, all red, walk, ped clearance, all stuff that we've already gone over. So you just enter your values right into those fields for each phase. Split. I said I would go over this earlier. So the split is basically the max time plus the amber plus the all red. So it's actually, it sums up those three together. So what you'll do is that your splits, if you had a very basic operation, northbound, southbound moves together, eastbound, westbound move together, and your cycle length was 90, for example, the splits would add up to 90. So if one split was 50, the other split should be 40. And those values will include the amber and the all red times. So you'll see that in VSTRO, just so you're aware. You really want to be looking at your splits. And the vehicle extension time, we went over that before, but that is required with running actuated phases. So in the case of the assignment, we would put a vehicle extension time in for phases 4, phases 5, and phases 8, because they're all actuated phases. All right, hopefully that makes sense. Then we've got the recall features. Coordinated, you basically identify the coordinated phases, which would almost always be 2 and 6. We're not going to touch on that today. We'll go over that next week though. Ped recall, min recall, max recall, we went over all that kind of stuff already. Basically, the reason I had you do those diagrams with the X's or the check marks was so that you could then do the same thing in VSTRO and understand kind of what that meant. Rest and walk, again, not going to really change your analysis in VSTRO, but it's just basically you put that on any phase that you want to rest and walk. So if it's a semi-actuated location, 2 and 6 would probably rest and walk. And then we've got dual entry. So compatible phases are served simultaneously, even if demand is only present on one movement. So to try and explain that in better words, if you came up to a 4-legged traffic signal, and I'm going to say at 3 in the morning, and the roads are dead, there's not really anybody around, and you're the only person on the road, and you're traveling northbound, by default, generally, if you're traveling northbound, the northbound green will be on, and at the same time, the southbound green will be on. Even if there's nobody there, you would normally have both phases being served simultaneously, and that's really just for safety reasons and expectations. So again, not going to make a bunch of difference in your analysis, but you should probably turn on the dual entry feature. All right, measures of effectiveness. I'm not sure if anyone's heard of this terminology before. Sometimes it's called MOEs as a short form. So vehicle and pedestrian demand will dictate the length of green time for each required phase to adequately serve the demand. And at semi-actuated locations, the green time required for the side street is often less than what's required to serve the pedestrians with the walk and the flash and walk indication. So if you have a really big intersection, your walk and the flash and walk might be 30 seconds, for example, but you might not normally need that much green time for vehicles, and you might only need that amount of time if someone actually activates the walk and the flash and walk, which is usually through a push button. So at semi-active locations, you could actually program your green time lower than the minimum pedestrian requirement, which will prevail if no pedestrians have activated a push button. So that again will be the difference between entering a max time and then entering a split time. But that's a little bit complicated. We'll go over that once we're in the software. And then you can use any extra slack time in the cycle to use to increase the duration of the walks. And basically, to sum up this whole page, just because we've determined that the minimum cycle length is 73.3, for example, or I think it was, 63.3 in the assignment, doesn't mean that's what our cycle is going to be. What we do here is once we enter all the data into Vistro, is we play around with the cycle length, play around with the splits until we get a scenario that seems to work. And there's really four things that we use to measure, four different options we use to measure what the effectiveness of our timing plan is. And that's going to be the first one, volume to capacity ratio. So simply, it's a measurement of the operating capacity of a roadway or intersection where the number of vehicles passing through is divided by the number of vehicles that could theoretically pass through at capacity. So it's V over C. And basically, once you hit the number 1, you're at capacity. So you always want to stay under 1. So it'll be in decimal places. So anywhere from 0.01, that would be so much capacity, to 0.99, which is basically considered constrained. So a general rule of thumb is you want to keep movements under 0.85. So that means under 85th% of their capacity, if that makes any sense. So you'll see the VC ratio as one of the options. Queuing. Queuing basically is a line or sequence of people or vehicles awaiting their turn to be attended or to proceed. So Synchro and Vistro show 50th percentile queues and 95th percentile queues. So 50th percentile is basically the average queue. So if you were in your model, if you had a queue at 50th percentile, that would be what you think would be the average queue, and 95th percentile is basically your worst case scenarios. So you use these outputs to determine if the required storage length of left turn or right turn lanes need to be extended, or if they're going to block the through lanes. And you can also, if you, let's say, have two intersections that are 200 meters apart, and you're showing queuing of 200 meters, you'll know that one intersection is going to back up into the other intersection. So you'll want to use the data for queuing to help you make decisions about how to allocate your green time. So in Vistro, you're going to see this little screen on the bottom right here, your 50th and your 90th percentile queues. One of them is going to show meters per lane. That's the queue length in meters. So in this case, we would have a 50th percentile queue of 54 meters, which would equate to 7 vehicles. So I'm pretty sure if you took, I haven't even done this yet, if you took 54 and you divide it by 6, which is the average length of a vehicle, then you get 9 vehicles. So I guess they're assuming that vehicles are, maybe some of them are trucks or whatnot. So they're probably assuming that there's an average length of more than 6 meters. But you could use both options to try and judge how well the intersection is operating from a queuing perspective. Again, top one is number of vehicles, and then the bottom one, the one below it, is number of meters, and then the 95th is basically your worst case scenario. So you expect on average, for this example here, you'd have a 54 meter queue, but worst case scenario, you might actually have an 88 meter queue. All right, hopefully that makes sense. Delay. So delay is a fairly easy one to deal with. It's basically just going to show you the delay per seconds per vehicle. And Vistro has basically 3 different delay options that it shows you. It's going to show you the delay per movement. So if you look at this top row here, delay per movement. So that's showing that if this was a left turn lane, the delay is 33.5 meters. And if it's a through lane, then the delay is 20.9. Oh, sorry, I meant seconds, not meters. And if you see the two the same beside each other, that probably means because the right turn movement, unless the right turn movement has its own dedicated lane, it shares delay with the through movement. So in this case, you'd have a dedicated left lane, and then here you'd have a shared through and right lane, which is why it's showing the delay like this. Then you've got the approach delay. So this 22.9 takes an average of this 20.9 and this 33 to kind of come up with an average delay for the whole approach. And then down here in the middle, between all of your different approaches, you'll see the intersection delay. So that's the average delay at the intersection. So 132, this example is not very good. You won't normally want to have the average delay of 132 seconds. That would be over 2 minutes. So obviously I've got some level service C's and D's here. So the ones I don't have shown, they must be much worse to make my average brought down like that. And then here's the easy one that seems to go well with the public, people who aren't in the traffic engineering field. They can relate to level of service. Basically, level of service A is great, and level of service F is a fail. So we don't have anything past F. Something can be a little bit bad and be level service F, or it could be extremely bad and it would still be considered level service F. And the level of service is basically is related to the delay. So if your delay is less than 10 seconds, you're level service A. If your delay is over 80 seconds, then you're level service F. And anything in between falls into these categories here. So hopefully that makes sense. And then I just have a little chart over here kind of explaining. So level service A would be the highest level of driver comfort. You have free flowing conditions. And then level service F would be the highest level of frustration and excessive delays. As a guideline, municipalities generally try to achieve level service D for through movements, but then will accept a level service E on maybe a side street or for a left turn movement. But you want to try and avoid level service F, but you can't always do that. I'm not sure about right now, but certainly pre-COVID times, driving home from Toronto, I'm pretty sure everything would be level of service F. Just too many vehicles on the road for the capacity that the road has. Okay, so this would be a good time for everyone to open up Vistro. And these are the 4 settings you want to check. I'm not sure if you've been in Vistro before, but once you change these 4 settings, some people might not need to change these at all. They may already be set. Then you'll be good to go from now on. So if everybody can open up Vistro.